So let's look at another example or revisit another example, which is the one that relates to balancing towers, as in the work of Watson. And let me remind you that we had three different approaches for computing these numbers. We first had a basic recursive procedure called towers, defined over here. Make it slightly bigger here. Um, like this. It was very important for this to work reasonably fast to put option remember. And what we found is that this was something that could get us very far, certainly much longer further than Watson. But we also found that if we ran this for a long time, we would run into problems mainly of memory nature. So we are moving into the territory where memory is actually a bigger problem than time. And this is something that sometimes happens very often when we write programs in experimental math. Um, Time is the big issue, and that's what sort of stops us from getting more information. Sometimes it stops us from getting the amount of information that we need in order to make reasonable conclusions. But other times the problem is memory, and even other times there's sort of a trade-off where we can choose between spending time and spending space. And actually, this is a good example of this because we found that we could save some time by being careful about what we committed to the remember table. So this is the mutually recursive D tower and R tower, where the whole idea is that the D tower program defined here does not come with a remember table. So that means that some things can be computed without being saved in a remember table. So we save space this way. But then the other one, um, the R tower, does have a remember table. So the idea is that when D tower works, it will call R tower without putting anything in a table. So it will sort of recompute it. And the whole idea of D tower is to speed up the computations in various situations where we can use symmetry, or where we can see a priori that there's not going to be any towers if the weight is too big, or we can use symmetry to say that if the weight is negative, then we compute the number with the positive weight and things like this. Now, if you think about the speed of these programs here, if you were to think of this theoretically, you can see that this is a program that calls itself recursively 3 times. And that is usually very bad, because that means that when you call the program, it will call itself 3 times. That will call itself 3 times, and so on. So you would expect to have a time growth which was 3 to the n. And that is actually what you would have if you hadn't the option remember in, right? Because the option remember will make sure that we don't recompute numbers that we already have. So we actually save a lot of time this way. And to get an idea of what goes on, we've done this before. Let me run dtower for 50. I get a fairly big number out. And let me show you figures showing what the remember table of R tower contains. Right, so you can see that we wanted to compute the number with 50 and 0, which is over here. And then Maple needs to compute some numbers. First of all, I mean, there's three values comparing, which comes from the three choices that you would have of going one to the left, staying on the top, or one to the right. Our saving, with the way we save time on symmetry, we only get the one which corresponds to moving to the right. So there's a value down here that we somehow need, but it's the same as this one up here by symmetry, so we can save that. And then you can see that what happens is that this it does grow quickly, but then it sort of stops growing, because over here we start seeing that these numbers are, the weights are now so big that it's impossible to reach it is possible to reach them. So getting the weight to be all the way out here is impossible if you only have a certain number of bricks to do it with. So we can cut down this expanding tree very dramatically by this line here. Right, and this line here, it comes from this uh, inequality here, and you can see that it's when the weight is bigger than n times n minus 1 divided by 2, so this is a parabola. Right, and then what you can actually do is you can say this here is, I believe, a straight line. So what you can simply say is that the number of calls in the number of values computed and put in the remember table is something that lives under a parabola and a line, and you can compute or estimate the number of values by simply computing the area here, right, which you do by completely standard methods, computing the integral and so on. And you can use this to see that the growth of the number of entries in the remember table grows cubically. So as the number of bricks to the third. This, of course, is something that takes a long time, and usually it's not worth doing it. It's much better to just look at the observations that you get, the time observations that you get, and say, well, that seems like it grows using a power law that looks like n to the 3. And usually you wouldn't spend time on making a detailed analysis like this, but it is possible. I mean, you could do it if you wanted to in many cases. So we sort of, and then of course I have to make a little bit of a leap of faith. I want to say that the time that I spend and also the memory that I spend grows proportionally to this area, or which is the same to the number of entries in the remember table. And of course that's also not quite true. I mean, sometimes you would expect that sometimes these calls will take longer time and shorter time, at least depending on the size of the numbers. So the numbers that you need to compute, they get bigger and bigger. Surely that must take longer and longer. And also storing it, because they get bigger and bigger, that will take longer and longer. So, I mean, it's not completely correct to say that there's a direct proportionality like this, but it's also not completely wrong, right? So you can usually do this. Also, I'd like to recall that we had a different way of computing these numbers, which is a little bit more clever, by sort of looking at various coefficients in a product of some polynomials, in an idea that reminded us a little bit of what we do when we work with generating functions. And this is something that I got out of the OEIS by looking at the early entries, and then somebody had put this in. And this was certainly a much better program than the one I have up here in terms of size. These are just essentially 2 lines. This is very short. But of course, and when we were looking at small values, it looked like it was just as good. But if we wanted to sort of really work out which is better, because we wanted to get many entries of this sequence, we would have to worry not only about time, but also about memory. And this is what I want to do in a little program here called extract usage. The way this program works is that it runs now, it's the towers version up to 100, and then computes and stores 3 numbers. And let me explain what these 3 numbers are. So you can see they're defined up here. So the first number is the time of the call, just like before. So I'm just running the program and I'm asking how much time it takes using the built-in function time in Maple. Next, I use length of up eval towers. So what is that? Well, towers is a procedure with a remember table, and when you run length up eval, you get the size of the remember table. This is counted in some sort of internal size used by Maple. I think it's roughly 10 bytes. So this will tell you how much how many entries that Maple have used in order to make this computation, and you can see that these numbers, they grow in a certain way. But then I also ask about this. And this is a little bit more complicated, but in order to understand what I mean by this, we have to think just a little bit about what does Maple do when it stores things. Because Maple is a program among many others that runs on my machine, and all these programs, they need to share the memory which is built into my computer. Right? And the way that it works is that every program will ask the operating system to get a certain amount of space, and then as a default you get a certain amount of space, and then if that's not enough, you go back to the operating system and say, I want to have more space. Right? And so then the operating system will give you that space if it has it. And then, of course, at some point, you're going to run out of space, and then the operating system will say, well, I don't have more space for you. Some operating systems will operate with slow space, so they will have, it will give you space that lives on a disk or something that's much slower than built-in RAM, and that is sometimes going to happen. But usually if you're in that situation, that your program is just going to be so slow that it's impossible to get something out of it. But what I'm asking here with this command, kernel opts bytes_alloc, is how many bytes are allocated by Maple at some point in this program. And what you can see is that when I run this program, at some point, it actually goes down, and then I think at some point it goes up again, and so on. So what's going on, this is somehow dynamically done, is that Maple keeps track of how much space it needs, and then if it sees, okay, I have more space stored than I need, then it will give it back to the operating system. If it has less than it needs, it will ask for more. And so this is really the thing that's important, is how much space does your program take from your computer. And that's also the boundary, right? So running into the limits is very different when we look at what consumption we have on the time side as compared to the memory side. Because when it comes to time, we're sort of flexible, right? If we really want to, we can run this program for a day, or we can run it for a week. Of course, we cannot run it for a million years, but somewhere in between, there's a little bit of flexibility. When it comes to time, you probably are interested in spending all this, when it comes to memory, you're probably interested in spending all the memory you have. So there's no need for your computer to save memory for other purposes. But of course, when you hit the limit, the program will stop working. So that's a hard limit, and you don't really care how much memory you're using, as long as you can stay under this hard limit. So measuring time is very easy, as we've seen. Measuring memory usage is complicated because it's not just some lists of things that we generate. It's also various kinds of overhead that Maple is generating. And that's very clear when we look at the Q and W program that we had, Q and T program, I think it was called, over here, that there is no memory mentioned. But of course, Maple computes these big polynomials and looks in various coefficients and so on. So this is completely opaque to us. We don't know how Maple does it, but we can see how much space Maple will ask for. And this is what I used this little program to get out. Right? So I could do the same for D tower and R tower. I could do the same for Q and T, but there would be no length op eval in that case, because these are not procedures with remember tables.